That worked great. Hello, I am Tom Jones. I'm a researcher at the University of Aberdeen. I work on internet transport. I currently work on an EU project which is trying to build a new socket API to replace the one we have that offers features and deployability and failover and automation. It's really cool. But before that, I'm going to talk about putting boxes on hills. So I started working at the University of Aberdeen in 2014. I was hired into the electronics research group where we do cool stuff with satellites. And at that point, we had gotten involved with the craziest UK funding idea you'll ever hear of. It was an interdisciplinary hub called .rural. The hub was made up of social scientists, ecologists, biologists, transport people, and by transport people I mean like cars and buses, not interesting transport, and social scientists. If you ever want crazy ideas, work with a social scientist. It's unreal. And as part of .rural, we did really strange things. So here we have a picture of the internals of a camera trap we built. The project was driven by some sightings on the Cairngorm mountain range in Scotland. There are sightings every year in a month of this really rare bird that people have been trying to track down forever. And they wanted to try and get some idea of what its mating habits were and how often it visited sites. And they looked at using commercial camera traps, but because we had all this funding, we decided to build something a bit more complicated. So I think this is one of the very early prototypes where we use microcontrollers and 6-LoWPAN. Later on, we replaced all this with a Raspberry Pi, an Arduino, cameras, activation stuff, and then we connected it all to a Hughes satellite modem, and we had a satellite link that it hung off. And what we did with this is we took it up the biggest mountain range in Scotland. And this comes with its own problems. This mountain range is covered in deer, not reindeer, but there are reindeer actually, but normal deer that run wild across here. The deer use any rocks or stones they come across to rut against so they can remove their antlers. So anything hard on ground level was going to be attacked repeatedly by angry deer. So you think, okay, well you just raise it off the ground and you have a flimsy base. But the Cairngorm mountain range also sees the highest wind speeds in the UK. The highest recorded wind speed in the United Kingdom was there, like the end of last year, like 136 miles an hour. And I don't know what you can't really see because it's quite small, but the satellite dish doesn't have any perforation because it gets to minus 50 C, so that would freeze and the dish would stop working. But it's just a big kite that you put on a mountain and then it gets like 130 mile an hour winds and stuff gets blown away. And this was really hard to work with. This project worked great. We could take pictures of mountains. We did live demos. The bird was never seen again. We have no idea what happened to it, but the camera took quite a good number of pictures of heather. If you don't know heather, it all looks the same. But yeah, so we did this. It was great fun to do, a nice piece of engineering. Doing this, we did a lot of satellite work, and we've done satellite work in the past. We have a long history of doing it, and we started looking at how video applications worked over satellite links. Satellite links are different than normal links because you're talking to something way up in space. You have round-trip times of about 750 milliseconds, so anything you do is going to see a massive delay. And the software that's being written for the internet just isn't prepared for this. There are bugs in Firefox where you can't use a satellite link that we fixed, but just having a strange set of links gives you strange circumstances. Along with satellite work, we do a lot of TCP congestion control stuff, and this is where I start to get involved. And a normal TCP connection has these states that are all time-based. We go through slow start, we end up in a steady state, and any loss we see is going to cause a big problem to our time. Slow start is an exponential growth phase for I have a picture somewhere. Slow start is an exponential growth phase. On a satellite link, it's being driven by AX on an RTT. So when you have a loss down and you have to slow start again up to the slow start threshold, you spend a lot of time. So when you try and browse the web over a satellite link and you have some loss, you have elements not load, and things get really messed up, and it's very hard to keep track of. And at this time, people decide to do TCP video over HTTP. So instead of using live protocols that can adapt to loss, Netflix and everyone decided that we would use TCP over HTTP because it always works, it gets through firewalls, NATs aren't a problem, this would be really great. But as the research community saw very quickly, the HTTP video is very awkward. There's a paper title that I'll never forget, Confused, Timid, and Unstable, about the congestion response for YouTube and Netflix. As soon as they see loss in the network, they go, oh, no, we'll slow down. This isn't working. Are quite pricey. What that's is an HTTP stream. You'll request a manifest over HTTP, which describes where the next chunk of segments are, and you'll download one of these segments. And based on the amount of time it takes to get the segment, you can decide whether or not to change rates, so you could have adaptive video bit rates. And the segments are timed so that they're not going to use the entire playback time, so that you can keep a buffer rolling. Hello. This leads to very bursty traffic. And when we look at this HTTP traffic over satellite links, we want to take as much as we can in a chunk. So we end up with long periods where our TCP connection isn't doing anything. And TCP is defined to close down there because we have a congestion window that, so we have a congestion window that describes this, but the congestion window is just a guess over a guess about the capability of the network. When we enter a period where we're not sending, this guess gets worse and worse. So we did work on something called NewCWV. NewCWV is an adaptation for rate-limited traffic. Rate-limited traffic is when the application is trying to send less than the network can provide. And NewCWV enhances something called congestion window validation, which is an older RFC. And we provide a new method for guessing how much is in the pipe. I got involved in this in 2014. The crazy social scientist we had in the project went to India instead of working. And I was a bit of a loss of what to do. We had PhD students, and one of my colleagues, Raf Losecki, had been working on this, and he had an implementation in NS2. We'd done simulation in the lab. We had an implementation for Linux. There's an issue in NewCWV that both Linux and FreeBSD have pluggable congestion control, but NewCWV needs to do this estimation outside of the congestion control mechanisms, so that we've not implemented something that is only applicable for New Reno or Cubic, so that we can do it below the pluggable layer. Of course, nobody wants to mess with the TCP stack like this, so it's very hard to deploy. So I did this implementation in 2014. I pushed it out publicly. I followed the drafts. Right now, the bug tracker says this, but who knows? I don't know what's next. Hiran is doing a lot of work on the TCP stack. There's one problem with this in that NewCWV needs packet pacing to really get a seen benefit, and FreeBSD doesn't have packet pacing in its network stack yet. Soon, I hear, but Randall at Netflix said this wasn't a problem because they had vendor drivers that would do pacing for them, so they could take NewCWV. We started talking about this in 2015, it's 2017, but this is only a month ago, so maybe we'll see something soon. So this is really just context for how hard it is to do things in the internet. We're trying to deploy a change to congestion control that will give benefit to most people. Google, Netflix, Facebook can do whatever they want. They have all this equipment, they can run their own hardware, they can run on private networks. They don't need these changes, they can pay people to do it. But anybody who's going to compete with them in the future needs these standardized changes. And if we figure out how to do these changes, we should be able to deploy them and get them going. But it's so hard to get this to move because the IETF doesn't want to do TCP changes. If you want to change the value of a field in an IP protocol, you're going to have a horrible time. It's going to take forever to get through the IETF. No one will deploy it in their networks, and then it might not work because it just might not work. This happened with ECN on the internet. It took like 6 years to get to the point where we decided we need ECN fallback, and now we're starting to see ECN marks coming through the network. I only have the slide because I think it's hilarious. There's someone on Twitter tweeted this, and if you press really hard, you can get more packets. So the changes we're proposing with the NEAT project come from a couple of core issues. One of them is trying to do this, but a lot of these problems come from how programmers see the access to the network. Rather than the reality we have, you know, someone connects to a router and it goes through the cloud and you get traffic at the other end. And it worked great, and it's all fine. But in real life, there's loads of stuff in the middle that's playing with your traffic that doesn't, it has its own agenda for what it wants to do. We have corporate proxies that want to break down TLS so they can see what you're doing. People injecting ads. Firewalls that not necessarily misconfigured, but configured in a naive way where we'll allow TCP port 8443, UDP port 53. Nobody uses anything else, right? But that just completely stops any deployment of new protocols. And of course, there are a lot of assumptions about how we get onto the network. In the past, when we designed TCP, it was for a very limited set of network access technologies. And the network technologies were very homogeneous, they were very similar. A 56K dial-up link is going to be similar to somebody else's. I mean, allowing for terrible phone lines is going to be very similar. But mobile technologies like 2G, 3G, 4G, you see wild spikes in latency, you see wild spikes in bandwidth, you see random loss, and the algorithms we have are designed to treat loss as a sign of congestion where we can stop sending, but everyone will know that they've been on their phone and the car moves 4 meters and you get a different model of what the network does because the tree's in the way anymore, and everything works much better. And then on top of this, we have the socket API and it's crap. You're all nodding, it's great. Write some code on Windows. So the socket API has done very well for the last 35 years, longer. Everything in the internet is now changed and it's different, but the access we have is okay. The issue really is that it doesn't offer any way to move away from it, and there's no way to move transport protocols. If you wanted to do something with like this series of calls that you had 2 interfaces and you needed to choose between them, you have to spend a lot of time around there. Okay, so why bother? Why not move everything into user space? Why not we just do it on top of UDP and we'll push it across the network and it'll all work fine. And this is happening a lot. SCTP, which is developed by Michael Tuxen in FreeBSD, offers a user space implementation that you can run over anything you can get a UDP socket on. And this is what's being rolled out in web browsers right now. So this is a new transport protocol on the internet, and it's running in user space, and it works. And this is what Quick tries to do. So Quick is Quick from Google is a transport protocol that sits under HTTP 2, and it offers nice, reliable streams, and you don't have head-of-line blocking between streams, and has some cool crypto stuff. But it's been developed by Google. We're 3 years since it was announced, and we have 1 implementation. The standards body is moving very slowly. They met last week. It's not really getting anywhere. And we have like Facebook pushed a draft last year about trying to do this generalized for UDP transport so they can build stuff that they don't tell anybody about. But we have the same problem where big players can do this. It's fine. Like, they can, will, and do whatever they want because they have loads of money. But nobody else gets to take advantage of this. And the openness of the internet and the web, it will really suffer if we do this. And there's also TCP over UDP, which is just raw insanity, and you shouldn't do it. So I work on this. It's quite complicated. This is the picture we sent to the EU last year. Yeah. Don't tell them, but we're not going to do any of this. We have a new API for accessing the network. It's event-driven. It's built on top of libuv. If you've used libuv, you know the networking stuff isn't great, so we have a nice consistent API for doing that. And we have a system for building and integrating new transport protocols that can run over the internet. So we can run this completely directly over the sockets you have. So we can run this over if you just have a system with TCP and UDP, Neat will run over this and you'll get some benefits, but not all of them. We can run on top of transports in userspace, so we can take advantage of the userspace SCTP library. And if Quick becomes a real transport protocol that's usable, then we can just plug it into the system because we've built an extensible model for doing this. And we have some things that allow us to apply magic to how we create connections. Over here, we have, just on the far right, we have two information bases that capture stuff about the network. And this is all mediated through a policy manager. Policy manager allows you to direct at a high level what you want from your transport stream. And the biggest thing we've implemented right now is fallback and homing over SCTP and TCP. So you can say at a high level that you want a reliable, ordered stream. And the policy manager can use information we've captured about previous connections, your interfaces, whatever else you might have, SDN orchestrators in the network, and we can do selection to find the best, some values of best, transport protocol that is available and is going to work over IPv4, IPv6, TCP, SCTP. We have this. You do one call, we get all of this for free. Applications are a bit smaller. They look like this. This one has the build-in. And applications work through the API directly into the Neat user module. User module is made of 5 pieces. We have a framework. We have the selection components that allow us to operate independent of transport protocol itself. We have the policy system. We have transport components themselves. So we have quite a nice abstract API for this. We have an abstraction on top of security protocols. So with Neat, by setting one flag in a policy and providing some certs, you can get TLS or DTLS for free with a nice API. There's no dealing with libSSL. And then we integrate with the network itself. Not only can we gather information from other connections that happen in the global system, but we can gather information from things you have in the network. So the characteristic information base that you have at the bottom here is actually just a set of JSON files on disk that describe the highest speeds you've got on an interface, the successful selection choices on an interface. But it can be fed in from other places, so we can look up MIBs and we can figure out what TCP congestion control algorithms you have and then provide that for selection from there. Or we could integrate with an SDN controller on your network, and the SDN controller can then say, I can create stuff for you if you need it. Like we can make a new interface for you, and it will work really well. And we have all of this implemented now. We have a demo from one of our partners, EMC, which does flow selection between small flows and big flows by specifying a file size. You say you have a small file and you get the normal 10 megabit link with low latency. You specify a high file size, and you get given a QoS mark that you set, and then you get your traffic directed over a higher latency but higher bandwidth link. And we're showing this to the EU in May. So we have demos for this working. Applications are very simple. So the architecture picture is really big and complicated, but it really boils down to almost nothing at all. Our connection state is metered inside a context. We have one context per thread. We're working on this right now. With this, we can then create flows. We have one single primitive for accessing the network. The application can choose its properties it wants to get for policy. The properties here are as a bit mask, which is what we had maybe a year ago. We now have properties defined as JSON, so you can build more complicated things. Set up some callbacks, and then you do an open. And you do an open, and neat just handles everything else for you. Great. And this is what it looks like. This is how it hooks in further. You get your events, and you do reads and writes. There are obviously issues between Datagram and Stream protocols, but we're an active research project, so we're trying to resolve all of this so you get a nice API. But this is as complicated as we want things to be. You set the property for security, you get DTLS, and it works. You don't have to figure out your cipher suites or your trust chain. We find the most sensible thing to do here. You want a transport protocol that's reliable, we give you a reliable transport protocol, and you just do reads and writes against it. I was asked in the last talk I just gave about the server side. If you swap out the open for an accept, the code is exactly the same. Obviously, the flow semantics are a bit different because you get given flows instead of having a flow, but it's all the same. You just get the unconnected event, and the code can be kept very, very simple. And because we're an EU project, we have commercial partners. One of our commercial partners is EMC. Another one is Mozilla. So I spent all week in plenary in Mozilla in Paris. And we're trying right now for our demo session to the EU in May to have Firefox doing selection between SCTP and TCP for a connection setup. We have this running on FreeBSD. If anybody really cares, they can bug Michael Tuxen and he'll say go away or come back in a week. What we get from this is incredible though. SCTP, if you don't know, you can have a look at it, but it offers multi-homing and multipath. So the demo we have is a file download through HTTP. And if you get TCP on your network, you get a normal file download. If you get SCTP on your network and you have multiple interfaces, you get multipath. We do CMT so we can share the connections from the application. You get twice the bandwidth. I think that's awesome.
Do you have parsing that can use multiple links?
Not yet.
Soon?
Someone's promised it to the EU, so. Yeah, and Linux. And we're developing all this on top of FreeBSD. So this is the main impetus for the talk is there's nothing FreeBSD specific in any of this. We could do this on any platform. It turns out because the SCTP stack runs on FreeBSD, it's the best place to run it because we have sensible networking and it's all easy and things compile properly. But we do continuous integration on all the platforms we support. If anybody can find a Windows developer, we would love one, but I don't think they'll let them outside. And we have builds right now, buildbots that you can find through our GitHub, running on ARM, FreeBSD heads, stable, NetBSD, OS X, and Ubuntu. I bet it was Valgrind that failed. Yeah, and we're a new project, so we're very open. All of the research we're doing is open access and being made available as soon as we can. All of the architecture and specifications we have, we're releasing as soon as we have them available. So if you want to read a 60-page document about why and how we'll stick this all together, we have it. Not interesting, though. And all of the development is happening in real time available. We have a public GitHub. We'll take patches from anyone. We really want patches from somebody. If you feel like fixing our documentation, then we're doing great.
Required by the EU project?
Yeah.
10% external contributions?
They want us to show that we have convinced other people to use this, and yeah. So I don't know how you measure this. Yeah, so all the code's online. You can go and have a look. It's really easy to check out. Very few dependencies. There are examples for how to drive everything. If you have some networking problem that you really want to solve with protocols, but you can't trust the network to be reliable, this will work for it. We are a year into development, so things are a bit janky. Later, we're going to do some bindings to Python and maybe Go so that you can access this through saner languages and you can use everything. But it's all there. Yeah, and that's me. I have loads of times for questions. Yeah.
I think this is amazing. I mean, this should be a keynote in large Unix conference, or something like that. I mean, this is really,
So can I just repeat that so it's recorded? I think this is amazing. I think we should be keynoted at large Unix conferences.
But my question is regarding, I see you using UV and you're using an event loop of UV. Are you using REPL of libuv? Because I've been running interesting problems with it with Node.
What's the bit you're having problems with? The REPL. Red pool. Ah. No, we're trying to avoid threads because they make things too complicated.
So when you're asking things with UV, do you do like async calls and callbacks?
Yeah.
And you wait for IO operations?
Yeah.
So that's transit
Yeah.
in UV. So you didn't have problems like only 4 threads and things like that and threads being stuck?
Not that I'm aware of. I don't. So the question is if we have issues with thread pools in libuv. I haven't seen any traffic in the issues from this. I think we'll get more issues as people try and do more, but we have Firefox running on this right now. So Firefox is a really big thing, and it's really, really stressed the code we've written. It's showed loads of bugs. It's been great to do. We've found loads of issues. It would be good to know. It would be good to have bigger workloads go through. We did some performance stuff, and we managed to push 6 gigabit through it. So it's okay as a networking library. There's no issue there.
How far along are the wrapper libraries for the languages?
They haven't been started. If you would like to start it. So the problem right now is we don't have a stable API. So even the example programs we have keep breaking. And you don't want to build on top of that, especially if you've got to deal with different languages. I'm hoping that in the next 6 months we'll have something stable enough that the demos we're building don't keep breaking. And I think the Firefox work we've done is going to force that to happen because Daniel Steinberg, the curl developer, works for Mozilla for us on this. And he's very annoyed every time we change the API. So.
Have you done anything around naming and addressing?
I think we're going to have to approach this. We spent a lot of time. So the 4 partners we have a tiny Norwegian company called Cellaway. We have EMC, Mozilla, and Cisco. And Cisco are very interested in being able to abstractly deal with names and do stuff like connect to a name rather than a service. At some point, the people from UIO wanted to get rid of port numbers. We talked them down. If you wanted to build something on top of a sane networking library that resolved the networking issue, you could definitely do it. We have a good DNS library integrated, and we have great DNS. But if you had a more abstract system, I think this would be a nice place to hook into.
Have you heard about Rena from Boston University, John Bears?
No.
Okay, you should have a look.
Okay.
And you wrote an awesome book that you can also give you the reference for.
Okay, cool. Thank you. Oh.
The protocol stack is called Rena, R-I-N-A.
I have heard of this, yeah. So the Rena protocol stack.
Yeah.
Yeah, I was asked this when I gave this talk last year, somewhere else. Yeah, there's tons of work in this space as well. We're not unique in any way. There's like 5 or 6 different projects that at different levels. People will have seen Brian Trammell's post-sockets draft that picked such a better name than we did. Yeah, so there are lots of efforts trying to fix this API because this is now being seen as a stumbling block. Okay, thank you very much.